All right, here's another video dealing with U substitutions. What's new in this video is we're dealing with definite as opposed to indefinite integrals. So you'll note that on your integral here, you have bounds, whereas in the previous video, you didn't have any bounds. They were indefinite integrals. At any rate, when you have bounds on your integral, it makes things a little bit more complicated. Turns out there's several different ways you can deal with these bounds. Your book tells you two different ways. Here it is, two different methods are possible, and what they refer to as another method, they'll say is preferable. I kind of disagree with your book here. The method that it says is preferable, I think is confusing. So I'm going to show you the two ways your book does this, and then I'm going to show you kind of a hybrid, I guess, sort of a modification of the first way, which I think is the easiest, and I'll leave it up to you, and you can do these however you want. So if you have this problem, the first thing you got to do is determine U and du. And that's hard in this problem. You should maybe even pause and think about what that would be on your own. This is one that a lot of students get wrong. What you'll do is you'll take advantage of the fact that the derivative of natural log of x is 1 over x. So if I let u equal the natural log of x, then my du will be 1 over x dx. So the x down in the denominator and the dx, all this stuff will go away. It'll turn it into the du. And the natural log of x will change into the u, and this will work out really nicely. The challenge is when you change your variables from x to u's, your bounds of integration are in terms of x's. So if u is the natural log of x, then when my x is e, I could say that the natural log of e is equal to 1. So this top bound up here, instead of being an e, it's now a 1. And similarly, using this equation right here, I could say that the natural log of 1 is equal to 0. So instead of my bounds going from 1 to e here in terms of the x value, they go from 0 to 1 in terms of the u. Right? Maybe this helps. The u's are 0s and 1s, the x are 1s and e's, and the way you get between u's and x's is use this equation which relates together u's and x's, says the u is always the natural log of the x. What I'm saying is that we can change this definite integral into the integral from 0 to 1 of u du. This is what your book says is the preferable method. Again, I kind of disagree. If you can get this far, now it's pretty straightforward. You can be like, well, the antiderivative of u, this is u to the first power. So I would call it 1/2 u to the second power, but then I still need to evaluate it from 0 to 1. And so I go and I plug in 1s, and I get 1/2 1 squared, and then I'd plug in 0s. I get 1/2 0 squared. I end up with just 1/2 as my answer. Right? None of this is new. The part that's new is we have to change the bounds of integration to make them in terms of u's instead of in terms of x's. I want to now show you the other way your book shows you how you can answer this same question. So I'll repeat the same question over here. This is the method that it says is not the preferable way to do it, but this method is really close to how I do it. It's not exactly the same. So I want to demonstrate this for you and then kind of tweak it a little bit to show you finally how I do it. And the short answer for how we're going to evaluate this definite integral this time is we're going to be like, I don't know how to evaluate this definite integral, but you know what I could do? This indefinite integral. If you wanted to know the indefinite integral of natural log of x over x dx, that wouldn't be an issue at all, because the only new issue here is when I have bounds and messing with my bounds. I do the exact same substitution that I did before, where u is the natural log of x, and then du is 1 over x dx, and that changes this integral into the integral of u du. And this is really easy to evaluate. It's just 1/2 u squared, I guess, plus c. Right? And you're like, oh, but you shouldn't leave u's in your answer because u is a substitution that you did. Fine, good point. 1/2 the natural log of x squared plus c. If this were just asking me for the indefinite integral, then no problem, I'd get this far. But it's not, it's asking me for the definite integral. But that's okay. If I've done all this work off to the side to figure out the indefinite integral, I can use that knowledge to figure out the definite integral because I have this thing called the evaluation theorem. And the evaluation theorem just says to figure out this definite integral, all I got to do is find the antiderivative of this function and then evaluate it at these two bounds and subtract the two. Where I already have the antiderivative of this function down here, it's the indefinite integral. So all I got to do is evaluate this thing from 1 to e. So I take this thing down here, 1/2 the natural log of x squared plus c if you want, and then I'm going to evaluate it from 1 to e. And you don't even need to write the plus c because you're going to evaluate from 1 to e, so the two c's would cancel out. And the way you evaluate it from 1 to e is you copy this expression, changing all the variables, x's in this case, into e's and then into 1s and subtracting the two. And because I made this problem, I made things work out really nicely. The natural log of e is just 1, because this is asking what power do you have to raise e up to make it equal 2. e in this case, so it's just 1. And the natural log of 1 is 0 because e to the 0 power is 1. So I get 1/2 times 1 squared. Sure, I'll write this one more time. Minus 1/2 times 0 squared, which just evaluates to 1/2. The same answer that I got before. It solves a given problem by first solving a different problem and then using that answer to solve the first problem. So you kind of have these two different trains of thought going. And sure, it works out fine. You get the exact same answer. The advantage to what we did here is you never have to change your bounds of integration. Right? We never had to change them from going from 1 to e to going from 0 to 1. We could leave them as 1s and e's all the way through the problem. The disadvantage here is that we don't have one linear stream of thought, right? Instead of this being equal to this is equal to this is equal to this is equal to this, so this is my answer. I say, you want to know this? Well, let me do all this work off to the side. After I finish that, I'll start back over up here and do this problem. Yeah. Anyways, let's do this a third time. Here's the method that I actually use for what it's worth, not to say that you have to do things the way that I do. If I saw this problem, what I would do is I'd start with my substitutions. And it probably won't surprise you to see that those substitutions are the exact same that they used to be. And then I'll go substituting these all in. So the 1 over x and the dx just change into the du. And the natural log of x just changes into the u. And I still have the integral of that thing. And you're like, be careful. It's not from 1 to e anymore. True. But I'm going to write that it's from x equals 1 to x equals e. I don't see the problem in this. Some teachers might have an issue with this. They'll be like, wait, why do you have x's and you have u's? Like, the reason I have x's and I have u's is because I don't want to change my bounds of integration. I want to leave those in terms of x's, but I've done this substitution to change my variables into u's. And you're like, well, you can't have an integral where your bounds of integration are in a variable different than the variable you use. And I'd be like, why the hell not? Who's going to stop me? I defined u right up here in terms of x. I feel like there's enough information right here for this to make perfect sense. Right, the x value is equal to e, and if you really feel like it, you could figure out what that is in terms of u, my variable, because I'm telling you the relationship between u and x right here. I think this is totally fine. If you do too, well then let me show you how you can continue this. We take the antiderivative of the u, which is still 1/2 u squared, and we'd evaluate that thing. But be careful, it's from x equals 1 to x equals e. And you're like, how do you evaluate this thing from x equals 1 to x equals e? Well, you change your u's back into x's. Right? You do the substitution that you'd expect. Your u's are the natural log of x, so this is just 1/2 the natural log of x squared, evaluated from 1 to e. Note I don't have to write x equals 1 to x equals e here, because if I leave off the variable that my bounds of integration are in, it's implied that it's the same variable that you see in this expression. The only reason I had to write x equals here and here is because my variable isn't an x, it's a u, so I want to make clear to the reader that the bounds, that I'm not evaluating this thing from u equals 1 to u equals e. At any rate, you plug in your numbers here, and it's the same step we've done a few times now. I get 1/2 the natural log of e squared minus 1/2 the natural log of 1 squared. And then because the natural log of e is 1 and the natural log of 1 is 0, this is 1/2 times 1 squared minus 1/2 times 0 squared, which is 1/2. The same answer that I got here and the same answer that I got here, just using a different method. Any of these three methods are totally acceptable. I think they all have pros and cons. Again, this is the one that I will typically use. Your book claims that this one in green is preferable to this one in red. But I don't know. The one in green is a little bit of extra work, having to always calculate the new bounds. I mean, in this case, it wasn't too hard to change my x's into u's, but maybe you can imagine instead of these being nice numbers like 1s and e's, they could involve harder numbers that would be more challenging to take the natural log of. You can avoid all of that by either using the method in red or the method in blue. At any rate, that's how there's a few different ways for doing u substitutions when you have definite integrals.